So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. So the transition from NITHEP to NITheCS is rushing ahead with great success. Yeah. So maybe I can share that we already recruited 37 non-NITHEP associates. Yeah, so that's that's starting to become an impressive number that will slowly change the character of what was NITHEP and make it the real NITheCS. Yeah, and this is also the reason why in the following weeks we will have more speakers not from the theoretical physics community. Today is a little bit of a mixed case. Yeah. Because also astrophysics and astronomy are now officially also part of NITheCS. So in this sense, it's a real pleasure to welcome Professor Kavilan Moodley from UKZN. And with us on the panel, you see there's also Professor Martin Bucher, who is an honorary professor at UKZN, but physically based in Paris at the École Normale Supérieure there. And Professor Sinaisky is our canonical co-host. So thank you, Ilya, for always supporting the NITheCS Colloquia and other events. And I've asked Martin, Professor Bucher, to kindly introduce Professor Moodley this afternoon. So Martin, if you would like to start, you're welcome to introduce the speaker today.
Well, thanks for asking me to make this introduction. So Kavi and I go back more than 20 years, and I'll just sort of summarize the main things. So Kavi is a native of Durban, and he received his bachelor's in honors from UCT in 1996. And then he went on to do a master's at what was then the University of Natal, before going to Cambridge, where he did a PhD in 2002, and then spent 2 years at the University of Oxford as a postdoc, before coming back to Durban, to UKZN, where he is presently full professor. So Kavi's research really spans a very broad range of areas in cosmology and the early universe, going from in the beginnings, more theoretical cosmology. His PhD was on isocurvature modes, and then he has done a lot of work on the observational cosmology, on the cosmic microwave background, mainly as part of the Princeton-led ACT collaboration, where he's worked on beams and galaxy clusters and lots of things. And more recently, he is a PI of the HIRAX project, International Consortium, which is led by UKZN. And that's what he's going to tell us about today. Well, it's a pleasure to have you here, Kavi.
Thanks, Martin, and yeah, thanks, Francesco. Thanks for that introduction. I think let me share my screen.
Please.
And let me just...
while you do that, just a reminder to the participants to use the Q&A facility to ask questions, and Martin and Ilya will manage the question session during and after the talk. Thank you.
Can you see that, Francesco?
Yeah, perfectly. Beautiful photo.
Okay. All right. Okay. Thanks. And yeah, thanks so much for inviting me to give this colloquium. So the topic today is on dark energy and cosmological cross correlations using HIRAX. So the picture shows a kind of cartoon version of what HIRAX would we aim HIRAX to look like in the Karoo Desert in South Africa. And using a technique called 21 centimeter intensity mapping, we aim, to constrain dark energy. I'll also talk about using this technique to also learn about cosmological cross correlations with other probes. So yeah, so I've actually, let me just say that I've assumed a kind of broad audience with a background in physics. So apologies for those people that have seen much of this before. I'll try to speed up, if people feel that it's too introductory. So let me start. Okay, so the outline for the talk is dark energy and I'll start with talking about dark energy, giving a context for this problem, and then how we use baryon acoustic oscillations to probe dark energy. I'll talk about how, in addition to galaxies, surveys of galaxies, we can also use 21 centimeter intensity mapping to probe the BAOs, so-called BAOs. I'll talk about HIRAX as an instrument, proposed instrument to carry out this program, and then what constraints we would expect on dark energy, if we use HIRAX. And in particular, a great challenge for this type of approach is foregrounds or the very bright galactic signal that can mask out this 21 centimeter intensity signal. And then finally, since we'll be mapping out the 21 centimeter emission over a large volume in the universe, I explore how this can be combined with other surveys in the Southern Hemisphere, for example, the Rubin LSST or the Simons Observatory, to learn more about cosmology and about these traces. So let's start with dark energy and baryon acoustic oscillations. So the mandatory kind of cosmic history slide, starts with the Big Bang. Radiation dominates early on. As the universe expands, radiation cools and matter comes to dominate. And during this epoch of matter, structure starts to form. The structure forms from small irregularities that were seeded, in the Big Bang. As these structures form, galaxies, and the cosmic web begins to grow, and you can see that shown here. Eventually, around about, at about a redshift of, just under one, dark energy comes to dominate, and this causes the expansion to accelerate. So that's the kind of high-level picture of cosmology as we know it. Of course, the devil is in the detail, and we can ask, what is this dark energy? Where did the Big Bang come from? There's lots of questions that are still unanswered. So a key probe that looks back to the beginning, very early on in the universe, so 400,000 years after the beginning, is the cosmic microwave background. And shown here is a kind of a map that's been made by the Planck satellite, which is kind of the state of the art in terms of all sky mapping of the cosmic microwave background. And what you see are these hot spots and cold spots, which correspond to underdense and overdense regions in the early universe. And this is the distribution of radiation or photons in the early universe. Matter also, the distribution of matter also suffered these in slight inhomogeneities. As we'll see, this gives rise to the this peculiar distribution of matter in the late time universe, which we're going to use as a probe of the expansion history of the universe and therefore dark energy. So you can take a spectrum of this, the kind of sky of the sky, so you can do a spherical harmonic decomposition. And shown here is the L, the multipole moment, L in the YLM, and the peak here is at a scale of about 1 degree, so L of about 200, and this just shows the power for that multipole moment. And what this means is that you can basically, if you look at the previous image closely, you'll see that the characteristic scale for separation of hot spots and cold spots is about 1 degree. And I think and this has been mapped out phenomenally by Planck. You can see the really precise measurement. You can hardly see the error bars on this plot. But what is key to notice is the sequence of kind of oscillations. And as I'll explain, these are present and very visible in the matter in the radiation distribution here, but we'll also see it at a much smaller level in the matter distribution, these so-called baryon acoustic oscillations. So it's simple to describe or to explain the kind of data with a simple model. It's basically a harmonic oscillator that's being damped and being forced at the same time, through the gravitational potential, and being damped by the baryonic matter that is coupled to the microwave background photons. So the beauty of this is that it's a simple linear physics that can explain the data that we see, and in particular, we can extrapolate or extract cosmological parameters with great precision because of this. So from this, as I mentioned, we can infer cosmological parameters, and what we find is that in these units of the critical density, so the density that will allow the universe to collapse, so that would be an omega, capital Omega of 1. We find that we don't have enough matter in the universe to cause it to recollapse. We only have about 30% of the critical density. And that so all these different probes from the cosmic microwave background shown here, from observations of type 1a supernova and from galaxy clusters that measure the matter density in the universe really well, we find that we actually live, we believe we live in a universe that has 30% of the critical density in matter and 70% of the critical density in this component called dark energy. And here this is shown in another kind of way, that dark energy makes up almost 70% of the energy in the universe, with dark matter making up 27% or approximately 27%, and ordinary matter only making up 5%. So this is the usual baryonic matter that we're used to seeing around us. So much of the universe is actually dark, and today we're going to focus on this dark energy component. The dark matter in itself is an interesting problem. So we can ask, what is the dark energy? And so this is the typical cosmic history slide. And dark energy, basically, we've inferred its existence by looking in this epoch here, so the late time universe, and observing the universe to accelerate in its expansion. So we can ask, what is this dark energy? Do we understand how it originated? What its properties are, and the reality is we actually have very little clue about it. The key challenge in explaining dark energy, and one can think of it as a vacuum energy, but there's a huge discrepancy between its predicted value and the value, from a kind of more fundamental particle physics model with the value that we actually observe in the universe today. And here's some quotes from some, I guess, famous people, indicating that dark energy is really an important problem and needs to be solved. So we haven't made a lot of progress on the theoretical front, and so the question to ask is it the cosmological constant, or is it something that is not constant in time and space? Does it evolve in time? Something like quintessence. And while theorists are grappling away with this problem, on the observational side, astronomers and cosmologists are charging ahead to try to measure the properties of dark energy and thereby, gain more insight into what its actual nature is. There's various ways one can probe dark energy. Supernova, where, type 1a supernova were used to measure the expansion rate of the universe and to discover that the universe is actually accelerating in its expansion, which won a Nobel Prize. There's cosmic lensing, which is the distortion of galaxy shapes, and galaxy clusters. So these are large collections of galaxies, and you can basically measure, how structure in the universe grows, which is sensitive to this dark energy. But today we'll be focusing on baryon acoustic oscillations, where one measures the angular diameter distance, as a function of redshift, so basically of the past history of the universe, and the Hubble parameters, so the expansion rate of the universe. So let's talk about baryon acoustic oscillations. So I'll just start this video. So basically, if one starts off with an overdense region in the early universe, it moves out, carried by photons, which moving at the sound speed, and at some point, roughly 400,000 years after the beginning, the photons were carrying the baryons with them, but then the radiation and matter separated, and each went its own way, which meant that the photons that were carrying these baryons with them basically dumped the baryons at a characteristic scale, which is just the sound speed times the time at decoupling, the so-called decoupling epoch, which corresponds to about 150 million parsecs, and a parsec is a few 3.1 light years. So this is a characteristic scale we have in the universe, and if one goes out and measures the separation between galaxies, one finds one can actually measure the scale, that there's a slight overdense region, and it's basically on this ring. You would expect to find slightly more galaxies than on either side. So I'll just move on to the next slide showing that. Okay, and so this is this has been mapped out. So we know that galaxies trace the matter distribution. So we can use galaxies to actually go out and measure, perform large surveys of galaxies, and then map out this feature. Now, recall that I mentioned 150 megaparsecs. This is actually a really large volume in the universe. So to do this, you need to map out large areas, and you need to go very deep or go to very high redshifts, so you collect more volume. So you can measure the BAOs using the visible light from galaxies. So you can use the galaxies as tracers, or the visible light in galaxies as tracers. So this program has been quite successful in mapping out the BAOs at low redshift. So I kind of showed you a picture from the Sloan survey, and basically, as I mentioned, galaxy positions trace these acoustic waves. So if you measure the galaxy positions, you will see a peak in the correlation function, as is shown here. So these are 3 different redshifts, going from 0.2 out to 0.75, and so you can see this characteristic peak. This is now plotted in units where you amplify the the feature. So this feature stands out, and you can see this feature is actually the BAO feature is quite well measured. And if you since this corresponds to a fixed kind of scale, if you work in the power in the spectrum, in the K space, or spatial scales, spatial Fourier modes, you find that you see oscillations, and this is where the name, the baryon acoustic oscillations, come from. So you can see these baryon acoustic oscillations mapped out by the Sloan 3 survey, right? And so it's these features that we want to measure with much higher precision and going to much higher redshift. So going above a redshift of 0.75, where we start to see dark energy starting to play a role, or dominating the expansion of the universe. So this recent EBOS measurements from the Sloan survey have actually mapped using a large kind of heterogeneous set of tracers, ranging from luminous red galaxies to quasars at higher redshift, and the Lyman alpha forest. I'm not going to go into these details, but basically think of them as different traces of the baryonic matter in the universe. And what they've basically measured are now ranging from a few percent to 5 to 10% measurements of the baryon acoustic oscillation scale. So that 150 megaparsecs that I'm referring to. So this is shown in H inverse megaparsecs. So H is about 0.7. So this is about 150 megaparsecs. So you can see that scale mapped out over cosmic time, going from a redshift of 0.1, so the very nearby universe, out to a redshift of 2. So we have we've got good evidence and good measurements for these baryon acoustic oscillations. So we'll now talk about probing the BAOs using another technique, not the visible light in galaxies, but the actual emission from hydrogen in these galaxies. So hydrogen basically, is the largest, neutral hydrogen basically dominates the baryonic budget in the universe. So it also is the fuel from which, galaxies form from, that stars are comprised of. So instead of, tracing galaxies using the visible light, we can also trace galaxies using neutral hydrogen, which basically, is found in the same galaxies and forms the fuel for the visible light. So shown here is an image basically to illustrate that, where these bright regions are in the cosmic web, you also find hydrogen. So we can in fact trace out the large-scale structure of the universe, not just in visible light, but also using neutral hydrogen. How do we measure the neutral hydrogen? We use the 21 centimeter emission. So this comes from the spin flip of the hydrogen atom. When the proton and electron have parallel spins, they're in a high energy state. And when the electron flips, and there's a small but non-zero likelihood of this happening, then when it flips to the anti-parallel state, it moves to a lower energy. Now, the timescale for this is very long, so you need lots of hydrogen to actually map out any, get any decent signal from these of these 21 centimeter photons. So we have a technique for mapping out neutral hydrogen in the universe using the 21 centimeter line. But as I mentioned, this it's quite costly. Well, firstly, mapping these galaxies individually in 21 centimeter is very expensive. It'll take a long time because the 21 centimeter line is so weak. But if we take a step back and think about it, we actually don't need to map individual galaxies. Galaxies are typically on a scale of a few hundred kiloparsecs or less than a megaparsec. And we don't need that resolution because the feature we're actually trying to map out is something on a much larger scale, shown here by this ring. So something on a 150 megaparsec scale, as opposed to a scale of these individual dots, which are galaxies. So we can actually trade off resolution for sensitivity. So this is the idea behind intensity mapping. We basically make a blurry map. So where we don't have very high resolution, we just have sufficient resolution to resolve this feature, the BAO feature. And so you can degrade, you can throw away spatial resolution while still measuring the large scale matter distribution and getting simultaneously information on the redshift. Since the 21 centimeter is a spectral line, you get the redshift for free. So this also makes it quite cheap, because if you have to do this with optical light or infrared light from galaxies, you first have to observe these galaxies and then take a spectrum, which can be quite expensive. So in this way, 21 centimeter intensity mapping can map out large volumes, by mapping out a large sky area and then over a large redshift range. It can, in principle, be a very competitive probe of the BAOs. And if we're able to measure the BAO peak as a function of cosmic history, then we basically have a standard ruler that can map out this expansion history, and then from that we can learn about dark energy and its evolution. Challenges for detection of this 21 centimeter intensity signal. And I should state that to date we have not detected the signal in autocorrelation. We've detected in cross correlation with galaxies, but there's significant challenges. The first is that the signal is weak, so we need lots of collecting area and very sensitive receivers. We need a large volume, because that will reduce the cosmic variance. Since the BAO scale is very large, we need many, many samples of that scale. We need to precisely calibrate our instrument, so we need a very stable instrument. And the biggest challenge we're facing is that the emission from the galaxy and from extragalactic radio sources is significantly larger than the 21 centimeter signal. So we're talking about of the galactic emission being roughly 4 orders of magnitude larger than the 21 centimeter signal. So you really need to understand your instrument, your measuring device, very well to limit the foreground leakage. We have, as I mentioned, we have detected the signal in cross correlation. So here shown here is an the image from Chang et al. 2010, where this signal was first detected by cross correlating the radio brightness with an optical galaxy density. And so we know the signal exists. It's just that we haven't been able to detect it in autocorrelation, crossed with itself. So one can ask, how do we go about designing a telescope to actually make this measurement? As I mentioned, we need sensitivity on large scales. So we need to use a compact array geometry. We need a large redshift range to capture a sufficient volume and also to map out the period of dark energy domination at about a redshift of 1. So these frequencies correspond roughly to 400 to 800 megahertz. Observational band. We need to map out a large angular scale. So the BAO is on a 150 megaparsec scale. So this corresponds to something like 1 to 3 degrees in this redshift range. So this then tells us if we want to build an interferometer to measure these scales, the baseline, the separations between dishes has to be between 15 and 60 meters. So again, something very compact. And then if we want to measure the BAO along the line of sight, because the BAO feature is a 3-dimensional feature, then that relies on having good frequency resolution, not angular kind of spatial resolution in the transverse direction, but good frequency resolution in the line of sight direction. So we need to map out, have a resolution of about 10 to 20 megahertz. So this suggests about 100 channels across this band. And we'll need more. In fact, we need more to measure the higher order peaks in the BAO and to remove foregrounds. And then because the 21 centimeter signal is very weak, so it's about, the signal we're looking for is at about 0.1 millikelvin, then we need a very low noise instrument. And for an interferometer that's characterized, or a radio telescope that's characterized by its system temperature and by the amount of collecting area it has. So we need a large collecting area and a very low system temperature. So all of these, and just to contrast the dense coverage that this kind of intensity mapping telescope requires with the kind of sparse coverage, random layout that Meerkat has. So talking about a sister kind of telescope in the Karoo, you need long baselines for resolution. So Meerkat has long baselines for resolution so that you can resolve these radio sources very well. So Meerkat is also has a dense core, a reasonably dense core, so it can measure structure on larger scales, by sampling the so-called UV plane, in the center here. So Meerkat is really, well suited to trace structure on small to intermediate scales. But we want to build something that traces structure on very large scales. And here, this is kind of a segue into HIRAX. So the hydrogen intensity mapping and real-time analysis experiment. The real-time refers to detecting transients like these mysterious fast radio bursts, which I won't go into here, but I'll focus instead on the hydrogen intensity mapping. So so HIRAX is the plan is to build a compact array of 1,000 6-meter dishes operating at 400 to 800 megahertz. Currently, we funded for 256 dishes. The dishes will be stationary to reduce cost, but they can tilt for more to build up more sky area. And the plan is to build these dishes in South Africa. And on the back end, there's a lot of overlap with CHIME, which is a sister experiment, which you've probably heard about CHIME because of all the fast radio bursts they've been detecting. And we're basically channelizing with these FPGA ice boards, and the backend correlation is done with GPUs, a large GPU supercomputer. So this is the team. I'm not going to spend too much time on this, but we've got significant funding on the South African side and from our partners abroad, from the Canadian and Swiss partners abroad. And as I mentioned, we have funds to build out in the first instance 256 dishes. We've got a number of South African and international partners, I should say. Location is important. So we're taking advantage of the fact that there's excellent infrastructure in the Karoo. So we have an MOA in place to basically build HIRAX in the Karoo. And shown here, next to, close to Meerkat is basically where HIRAX is going to be. So it's along the main road, so it's easy to get to. And there's also a power and data line running by, which we will basically tap into. And then the other advantage here is that in our band, so this is a measure of the RFI, radio frequency interference at the HIRAX site, and you can see that our band is actually superbly clean, which makes us very competitive. And another advantage is that we have access to the southern skies. So I'll talk about that when I talk about cosmological cross correlations. So I'm not going to spend too much time. Well, I should say there's other HIRAXs, in the Karoo. So we have the rock HIRAX or DASI, and that's our logo. So like the Meerkat, it's a resident in the Karoo. And we didn't know this at the time, but you need to misspell your experiment so that you can Google it easily. And we didn't realize there's a trash metal band also called HIRAX. Yeah, so moving on. So I won't spend too much time on this, but basically, we have the instrument is a 6-meter dish where we've basically got dual polarized feeds, and then we carry the signal from the dishes to the processing backend over optical fiber. So we have these radio frequency over fiber transmitters and receivers, and then we basically digitize the signal, channelize it, and basically do the cross correlation. So the channelization and basically we do a corner turn here, this F engine, where you take different channels from the same channel from different telescopes and combine them. So it makes it easy to do the cross correlation, and the cross correlation is done in this GPU X engine. So this is a picture of what certain parts of the instrument look like. These are composite dishes and metal dishes built in South Africa. And yeah, let me not spend too much time, but I'll just call out that CHIME, is a kind of sister experiment. It's a cylinder-based experiment, so it has different systematics. And while CHIMEs can see the whole sky each day, HIRAX will only integrate on narrow strips, but it can then integrate deeply on these narrow strips. So there's different pros and cons for both approaches, and I can talk more about that later, but I want to get on with it. So so we've got our prototype array at HartRAO, so that's the background, my Zoom background as well. And so we've been doing a lot of prototyping, understanding the system. We've also installed the two prototype f.25 dishes here. So here I'm standing in front of the fiberglass dish, and we're now back after a year of being off, are back at site, doing more work on these prototypes. And we're testing the RF over fiber system, and also testing these dishes. And I should mention there are complementary prototyping efforts, both at the DRAO in Canada and Greenbank, and also more recently at Baryon in Switzerland. So all our partners are actively involved in prototyping and developing the instrument. So we can take data from on site, and the instrument is working. However, there's a lot of RFI at Hartbeeshoek. This is just outside Johannesburg, this site, and we are going to shift our prototyping efforts to the Karoo. We've got a qualification site or qualification array site where we're going to qualify our first two dishes before we move to our main site. So this will help significantly with characterization of the instrument. As I mentioned, we really need to characterize the instrument with very high precision. And this effort is also going on at DRAO and at Greenbank and at Baryon. So this is a kind of the quick view of our schedule and our plans, moving forward. And I've revised these dates now, to be in line with COVID, and we may have further slips due to COVID, but we're hoping not. We did put out a tender for the dishes, and we're working on a process to get the local companies involved to actually make these dishes for us. So I can say more about that if people have any questions, but let me move on to the cosmology side of things. So talking about, let's talk about how HIRAX can measure dark energy and how we're aiming to overcome this foreground challenge. So this is basically a cartoon of what single dishes, map out. So you're just using the auto correlation of a dish versus cross-correlating dishes, which these are the scales that the interferometer maps out. So basically, what the goal of the survey is to map out 15,000 square degrees, and by tilting the dishes, we build up the sky area, and we have a wide redshift coverage from 0.8 to 2.5. So these give us angular modes. So these are the kind of spherical harmonic Ls from 40 to 2000, and then in the radial line of sight, we also have a large range of modes that we measure. For people interested in transients and sources, our basic daily sensitivity is 15 microjanskis per beam. So that's the typical survey, that we'll carry out with the HIRAX. How well will we measure these BAOs with HIRAX? And I should say what I'm plotting here are these K perpendicular modes, so they related to L. So these are basically the modes in the transverse direction, so across the sky. And then K parallel modes are modes in the parallel direction, so along the line of sight. Or as we change frequency, we probe different slices of the universe. And so shown here is the sensitivity per pixel that we'll aim to measure the BAO with. And you can see that, just from this number, roughly about 30 to 40, we've got a significant amount of sensitivity per pixel. And this translates for the 1024 into basically, percent level measurements of the distance scale over a few percent measurements of the power spectrum and this BAO feature, as you can see here. And then that translates, as I mentioned, into measurements of the distance scale. So this standard ruler that we're going to use to probe dark energy. And that distance scale, if you Fourier transform this feature, you basically get a peak, as I mentioned, and that corresponds to the distance scale. So we're going to make high fidelity measurements. Well, we have sensitivity to do that. We still have to overcome the foreground challenge. I should also point out here that we actually measure scales from 0.01 to 0.1 very precisely, and I'll come back to that later when I talk about cross correlations. So these are the forecasts for the distance scale. So you can see that HIRAX 1024 will measure the distance scale. So this is you can compare to the plot I showed you earlier for the latest kind of state-of-the-art measurements. And so we'll be measuring the distance scale at the 1% level over the redshift range we cover. And unlike this, the EBOS results where they're using a heterogeneous sample of probes of the BAO, this will be a single probe of the BAO across this redshift range. So we'll have percent level measurements of the distance scale, and we can then turn those into constraints on cosmological parameters, in particular dark energy. And the way we characterize dark energy here is in terms of an equation of state. So W is the ratio of the pressure to the energy density. And for a cosmological constant, we expect W to be -1 and not changing. Whereas if we had dynamical dark energy, we would expect some evolution in W. So W naught is the value today, and WA is a linear change in the basically in the expansion or the size of the universe. And so this is one model that describes this equation of state of dark energy. You can choose non-parametric versions, etc. But at least it gives us a handle on which to compare different probes. And so we'll basically and there's something called the a figure of merit, which is basically 1 over this error, size, the area of this contour in the WA and W naught plane. So 1 over the size of this contour is called the figure of merit, and the larger it is, the better your probe of dark energy. So HIRAX will provide tight constraints on dark energy. For the 1024, we're looking at measurements of W naught, which are at the few percent level, and measurements of WA, which are at the 10% level. So that is very competitive in terms of constraining these models, and that's shown here. And just in terms of state of the art, using the current Sloan measure or EBOS measurements, you can see that these error contours are quite large. So this will be a significant improvement over that. HIRAX, the figure of merit, is about 300. So this is approaching the stage 4 class Galaxy surveys. So much larger surveys, and done at much less cost because of the advantage of the 21 centimeter intensity mapping approach. So this is the kind of ideal situation, what we would get if there weren't any difficult challenges along the way. And the biggest one is foregrounds. So shown here is a kind of plot from Shaw et al. 2015, where we basically show the level of the signal that we're looking for. So we're treating it as a Gaussian random field. You can see that this is at the millikelvin or 0.1 millikelvin level, whereas the foregrounds go up to, depending where you look, but tens of Kelvin. So there's many orders of magnitude that separate the foregrounds, the unpolarized foregrounds, from the 21 centimeter signal. The polarized foregrounds are weaker than unpolarized foregrounds, but still significant. And what's actually shown here is the kind of approach that we're going to take. We expect the unpolarized foregrounds to be smooth because it's synchrotron emission. We expect the spectrum to be smooth. That could change depending on which position on the sky you're looking, but assuming that the spectrum is smooth, then that means as we change in frequency, and that's shown here, we can represent the change in the foregrounds by a polynomial function or a set of low order kind of basis functions. And what this means is that if you high pass filter the signal, the sky signal, you'll actually remove much of the foregrounds. And as you can see, the structure in the signal is much noisier and all exists at much higher frequencies. So by doing a low pass, high pass filtering of the sky, we basically aim to remove the smoothly varying foreground signal, and what will remain is, we hope, is the 21 centimeter signal. Of course, that's making a number of assumptions, including the fact that we assume that the polarized foreground it doesn't have higher a smaller scale structure, which may not be the case. That's being explored at the moment, and of course that we understand how the instrument basically maps the sky into the observable, and that also is an assumption which needs to be verified. And I think this first generation of 21 centimeter intensity mapping experiments is aiming to do that. So when you do this filtering, you actually lose the very low frequency K parallel mode, so the modes along the line of sight. And you can see this here. So with the full foregrounds, you lose these modes, but you actually retain your sensitivity to the BAOs. So even though the galactic signal is several orders of magnitude larger, you can give up on these low frequency modes, but still recover your BAO cosmology. At least that's the hope. The challenge is, as I mentioned, is that your instrument, so you can basically write the equation as the visibility, which is measured by the radio interferometer, is just what is called this function, this transfer function B times the signal A plus a noise term. And so what I've shown here is basically the fact that the instrument has errors in it, and the foregrounds, we can make a model for the foregrounds, but there'll be deviations from it. And so the thing we're trying to pull out is this B times A, and what's in the way is the smooth foreground times the smooth instrument if response, which you can filter out, but you're still left with the kind of small deviations in the foregrounds times the smooth instrument response times this smooth foregrounds times the deviations in the instrument. So these terms here in red can really mess up your recovery of the signal that you're looking for in blue. So you really need very precise foreground modeling and characterization, and you really need precise knowledge of the instrument. So you need to characterize your beams, so the pattern that the telescope and the your antenna makes on the sky, where you are pointing, the delays that you experience in the interferometer, and then how the instrument responds in terms of the gain in the signal, the spectral behavior in terms of a bandpass, how the signal, if there's any cross polarization. So there's a lot of technical details, and shown here is if you make an error in the beam, so the pattern on the antenna pattern on the sky, at the 0.1% level, it's okay. But when you get to the 1% level, you really start, so this is basically the ratio of, the noise to the signal, and you start seeing the noise building up, basically. So this is a leakage. And so, you have to be in your instruments at the order of the 0.1% level, which is a really extreme precision in terms of, understanding that. So we've been working on, various approaches to this, you're doing external calibration using holography and a drone mapping. And so this is something we're trying to test out in the field, looking at analysis techniques to look at non-idealities in the telescope, and also doing, serious kind of design simulations, so we can set tolerances on our telescope parameters. So for example, how well aligned our dishes are, how well placed is our focus, dish by dish, all of these to, basically make the instrument as ideal as possible so that we limit this instrumental leakage. So basically to make this term here, this delta B term here, as small as possible. Okay, so, so we've been working on this simulations for instrument design, where we include various systematics. So, we map this transfer function up here, acts on the sky to get our observed visibilities. And, we've got this process for including systematics and then calibrating out these systematics to see what kind of sky we recover. And we've used this very successfully to try to understand how sensitive, we have to design the instrument. For example, the telescope, how, how accurate must our pointing be, how accurate must our beams be, and, how accurate must our baseline separation be. And so shown here, is basically, well, here, so we have an end-to-end simulations pipeline that incorporates, simulated beams from full electromagnetic simulations. And we use this simulations to set requirements for the dish tender to control errors in our beam shape pointing and the baseline delay. And we've adopted a Fisher matrix approach to do this, and to determine the instrument tolerances that will allow us to mitigate this foreground leakage. And so shown here is this kind of recovery in the K perpendicular K parallel space. When you run this through, when you introduce a perturbation in the placement of the focus in the Z direction, so away from the dish, you find that you need to place your focus, so where your feed basically, within 10 millimeters, and at that level you start your systematic error from not understanding your instrument starts becoming comparable to your thermal noise, so your noise error, and that starts ruining your measurement. So we've carried out this kind of successful exercise to set this, and we've used that to set our design requirements for the dishes that we're hoping to build. I'll stop there on talking about dark energy, and I'll move on to cross correlations. It looks like I probably have a few minutes left. So Martin, would it be okay to finish up on these cross correlations?
I think so, yes.
Okay. All right. So so as I mentioned, HIRAX has excellent sensitivity for the scales that we measure, and comparing to some Galaxy surveys and even SK and Meerkat, you can see that we well optimized to measure these BAO scales, and it's even competitive compared to some satellite and ground-based next generation Galaxy surveys. So because we have this great sensitivity, and because we overlap with these other many of these other surveys, so for example the legacy survey of space and time, the dark energy survey, a little with DESI, but with Euclid and WFIRST, and also on the CMB side with the ACT the ACT, SPT, and Simons Observatory, it's interesting to consider, what can we learn by combining all these. Many of these experiments will be making, large area observations in the southern sky. So, 10 to 20,000 square degrees that'll overlap with HIRAX. So what can we learn by combining these data sets? And cross correlations, as I showed you before, it's ideal for testing systematics. The first 21 centimeter detection was in cross correlation, and then also for doing joint science. So I've been involved in a few different kind of applications of this cross correlations. The first is trying to calibrate redshifts for the Legacy Survey of Space and Time, so the LSST, because we have such great spectroscopic resolution in terms of our frequency channels. We can actually, and we cover the whole LSST area or most of it. We can actually calibrate the redshifts of the galaxies using a cross correlation technique. And what you find is that you actually can then reinstate the accuracy with which you can measure dark energy, assuming this self-calibration or technique, or technique with compared to a technique using calibration from the 21 centimeter. So that's an interesting application. Another application is cross correlation between galaxies. So the magnification bias one sees in galaxies with 21 centimeter. And the idea here is that to first order, the 21 centimeter is not lensed. So if you use a 21 centimeter as a foreground tracer, you'll be sensitive to the lensing of background galaxies. But if you reverse this, that's you have an unlensed sky, and you can take advantage of this to construct an estimator, which improves your current estimators by a factor of about 2. So that's an interesting application of using the fact that the 21 centimeter is not lensed first order. And then some work I've been doing with a student here at UKZM and another in Princeton, another postdoc. So I think Warren actually is on the call, is correlating the 21 centimeter signal with CMB lensing. Now the challenge here, and I'll explain this very briefly, I can go into more detail. The challenge is, as I mentioned, when you remove foregrounds, you remove your low K parallel modes. So anything below 10 to the -2, which I've kind of indicated here. So most of this signal in the CMB actually comes from these large, low frequency or large scale modes. So when you actually remove these modes in the 21 centimeter, you remove most of your signal. So this quantity, the direct cross correlation, actually vanishes. To recover it, we take advantage of the fact that if an overdensity on small scales is sensitive to the background density in the universe. So if you're in an overdense region, this density will grow more significantly than if you're in an underdense region. And so what this means is if you have these small scale modes, so the high frequency modes, and you correlate them, you're actually sensitive to the large scale modes, which you've actually lost because you remove them due to foregrounds. And so if you take 2 copies of these small scale modes and correlate them with a large scale mode, so in this case, we looked at CMB lensing, then you can actually recover this cross correlation. And basically, this estimator relies on the modulation of these small scale modes by large scale or super sample modes. And so we can recover this correlation, oh, sorry, this is behaving badly. Right, so we can recover the correlation. Oops, sorry. There we go. So we can provide, in doing this, we can provide tight constraints on the bias of the H1, so the clustering of H1 relative to the dark matter. Okay, sorry. Let me just, we can then independently constrain the growth function in the universe and the clustering amplitude. So usually these parameters are degenerate, but by combining the auto spectrum and the bispectrum, we can break that degeneracy. And then finally, and this video is playing, sorry, we can improve dark energy constraints. So you can see here by including the bispectrum in addition to the auto spectrum, we can shrink our error bars on the dark energy parameters. So I think I'll stop there, given that I've only got a few minutes left. So thank you very much.
Yeah, thank you very much, Kavilan, for a very, very fascinating talk, and thank you for putting South Africa again on the map of astrophysics and cosmology with this new exciting experiment. Let me ask Martin and Ilya to guide us to the Q&A session. Martin, would you like to start?
Well, I guess we don't have any questions yet on the Q&A or in the chat that I can see. So
there was a question, Martin.
Sorry, we have one. We have one, yeah. Could you compare the single dish mode, like Meerkat survey, or interferometer mode, the advantage and the challenges of each? Thank you. Or Meerkat survey.
Meerkat, yeah. Yeah, so Meerkat is a proposed intensity mapping survey using Meerkat. So there, and actually I can go back, if I may, to the slide I showed earlier. And I'm not sure if you can you see this?
Yeah.
Yes.
Plot? Yeah. So you see that, so Meerkat is shown on here. So Meerkat will have excellent sensitivity on very large angular scales, and again on very small angular scales. So this is using interferometer mode and using single dish mode here. So the problem is that the BAO scale just kind of falls, unfortunately, just in between these two modes. So the Meerkat survey, won't be very sensitive to the BAO. Well, not as sensitive as HIRAX, for example, but it would be able to do excellent science on very large scales. So, for example, mapping out large scale features in the 21 centimeter distribution, which have other applications, and then also mapping out galaxies on small scales.
Okay, thank you.
do you see any other questions, Ilya?
I think
Inji raised his arm.
we can allow him to already done by Ilya. Thank you.
Okay, hello, can you hear me?
Yes.
Hello. Yes. Okay, great. Thank you for the very nice talk, Kavi. And there is
Thanks.
a plot by Devon Creighton that you cited at the fairly late stage of the presentation.
Right.
Maybe the last fifth such.
Wait, hold on. In the dark energy, this one?
Yeah,
this one?
yeah, this one, yeah. I wonder what is the, the right panel, quite a D Creighton. I wonder what is the black dash line?
Oh, right. So that's the BAO, basically the range. We hope to measure the BAOs. I can just show you this in another kind of slice. It's the scale here, basically, here to here. So in radio, plotted radially. So it's whatever 0.01 to. Yeah.
But why does that? Well, why
Sorry?
does like why that line is like a bending curve? Why the line is like the shape as is shown? Yeah.
Oh, it's a constant radius. So it's the k squared is k parallel squared plus k perpendicular squared. So if you have constant, k squared, yeah, then it's a radial plot. So it's like basically like cylindrical power spectrum.
Okay, great. And the other question is that for your cross correlation part, you mentioned the previous work of LSST correlation, forecast of LSST correlating with HIRAX. And you said this will help to determine the redshift of LSST. But I wonder, will this technique be able to determine each galaxy sample of LST, or it's like determine a group of sample? What is?
It's
what
a
do you mean by,
yeah, it's a statistical technique. So we'll be we're basically determining these redshifts, the redshift distribution statistically. So more strongly constraining the form of the redshift distribution of the underlying galaxies, which is needed for the lensing, for example. So it's not individual galaxies. Yeah.
Okay, thank you.
Can I ask a quick question while maybe the other participants come up with more questions. Just out of curiosity, Kavi, is there any particular dark energy theory that you would like to prove, or is there any dark energy theory that you don't like that you would like to disprove?
I think the first step is to establish whether the equation of state is consistent with -1, for the large range of redshift, as much as the over a large range of redshift as possible, and then that will tell us if we're looking at something like the cosmological constant.
Yeah.
It's either 0 or non-zero, right? Obviously, but so it has to be there or not, and whether if it is there, is this what we're seeing, or if I think the hope is that maybe we see something which is different from -1, and then statistically significantly different from -1, and then we know that there's something dynamical. And I think as a first step, that would be a major step forward.
No, that would be very interesting to see. Yeah, no, thank you. Are there
I do
any?
not see any more questions or raised arms.
Okay. And do the two other panelists have questions?
I have a question. Do you want to, are there any sort of future experiments beyond HIRAX, or how do you see this sort of intensity mapping going on into the future after HIRAX is done?
So I think there will be there's certainly great interest for these compact arrays. I think at the moment these are largely being driven by the science case related to fast radio bursts. So the fact that you can actually detect lots of fast radio bursts makes a strong case. So for example, in Canada, even they've got CHIME, but they've now funded CHORD, which is a dish kind of follow-up to CHIME. With the primary science case being fast radio bursts, but they're also planning to design the instrument to be able to tackle measure baryon acoustic oscillations with 21 centimeter intensity mapping. So I think there is a future moving forward. There's other experiments around the world, Tianlai in China. There's a number of pathfinders, so to speak, that that are moving forward. I think this first generation will learn the kind of difficult lessons, maybe not get to a detection. I should also mention at the very much lower frequency range, there's experiments like HERA that are also trying to do this, NSK that are also trying to do this. So I think once a detection in autocorrelation is made, then I would expect the kind of floodgates to open, and because then that would verify this as a method to very cheaply map out the three-dimensional structure in the universe compared to galaxy optical or infrared surveys. So I think once we cross that threshold, I think there'll be a much larger investments made. I can tell you that the US is, or at least there's a community in the US that are proposing to build a small and then large version of dish array. So small being 5,000 elements, and then large being 30,000 elements. So this is at the end of this decade, so in 10 years time. So there are plans to do this. I think whether those plans get funded or not depends on how these Pathfinder experiments perform and what they find.
Okay, thank you. We have a question from Ajit Sampath. Some of the audience might wonder why we choose dishes instead of dipoles. Since we are talking about low frequency radio, it would be nice if you could clarify this.
Yeah, so I think the approach we're taking here is that we want Dipoles, I think the challenge, in my view at least, even though SK low is adopting this technology, I think with dishes, as we've seen maybe compared to cylinders, we have more control of the beam, so the antenna pattern on the sky. And I would say that you really need very strong control. Whether the dishes we're building now are good enough is another question, but I think you'll get better control of the beam patterns, by building dishes. If anyone has any follow-ups to that.
Okay, thank you.
Yeah, Kavilan, if there are, sorry. Yeah.
I think Inge wants to ask one more question.
Okay, sorry, Inge.
Oh, yeah. Hi, Francesco. I just want to take this chance to answer the question that you have just raised, which is about dark energy. I mean, I have that theory of holographic dark energy, which I believe the universe is just like a black hole. And we make prediction that the low redshift evolution of Hubble constant, Hubble parameter should be slightly faster than the lambda CDM, whereas at early stage it could be slightly lower. So that is able to explain the local Hubble constant puzzle. So my model will be able to be distinguished, or verify or ruled out, I think in a few years' time, if the low redshift data like the DAISY survey or maybe the HIRAX or Meerkat that be able to measure the low redshift BAO. So yeah, so I just want to shamelessly mention that I have a theory of dark energy. Yeah.
Okay, no, perfect. Thank you, Yingche. So in a year or two, we'll invite Kavilan again.
So maybe
tell us who's the winner.
So maybe this experiment will confirm the UKZN kind of led theory.
Yeah, no, that would be
yeah, that would be fantastic. Yeah.
Okay, then on this very optimistic note, yeah. So thank you, Kavilan, again for
Thanks very much.
Really exciting talk that seems to be of interest to many people, in particular those who develop dark energy theories. Yeah, and thank you very much to Martin and Ilya for the introduction and the moderation of the section of the questions. So Kavilan, again, thank you very much, and we will pencil you in a couple of years' time for the results.
Yeah. Okay. Thank you, and thanks to all the audience for listening.
Thank you very much to everyone, and please keep staying safe because COVID is out there waiting for us who are not yet vaccinated. Yeah.
All right. Thanks. Bye. Bye.
All the best. Bye bye.
Thank you. Bye bye.
Bye.